Thank you very much, Imar, for this nice introduction. And it's actually very nice to see you again, although it's only on the screen right now. So can you see my presentation?
Yes, clearly.
Good. Then I will select my pen. There we go. And hopefully you can see my presentation. So what I would like to do today is share with you some of the research we are doing on improving rice and cassava for human health and also for industrial applications. Most of you know that rice and cassava belong to the 10 staple crops that I call the staple crops that feed the world. So if you look here, for example, at maize, rice, and wheat, they represent, these three crops alone represent about 50% of the calories that are consumed by the entire human population. And you see that they are also produced in large amounts, just like cassava. Of course, the nutrition is not equally distributed about the world. There are some parts of the world that have less calories available for nutrition. Other parts of the world have too much, as shown here in the dark red. That's where I am right now in California, in the United States. No, come on. If you look at these staple crops, even though they feed a large percentage of the human population, rice, wheat, and cassava, they don't really have very good micronutrient levels. So these are the micronutrients like iron, zinc, and vitamins that you need for a healthy life. So, for example, with rice, you can eat a lot of rice. You don't feel hungry because you get a lot of carbohydrates. We just heard from Professor Lee about the cellulose, which also contains a lot of energy. So carbohydrates contain a lot of energy, so you don't feel hungry, but you don't get the micronutrients that are essential for human health. Other crops such as maize and potato actually have quite favorable micronutrients levels, but cassava and rice have not. So we have actually decided to improve the nutritional qualities of these crops because micronutrients you can take up by various ways. So most of us have actually a very balanced dietary intake. So we eat a lot of vegetables, but also meat. And these provide usually all the micronutrients that we need for a healthy life. But for those people who eat a lot of staple foods, such as rice or cassava, for them, food fortification with micronutrients might be necessary, but this often leads to products that don't taste very well. It's not palatable to consumers. So the alternative would be to take supplementation. So you take vitamin pills or iron tablets in order to reach the levels of the micronutrients that you need for your body. But the scientific community and also nutritionists have decided that the best way actually to provide the micronutrients to the human population is through biofortification of crops. So if we just look at the problem of iron, many people in the world suffer from iron deficiency. It's also called anemia. This is not only a prevalent issue in developing country, and as you see here also in Indonesia, iron deficiencies are quite prevalent, but it is also a problem in developed countries. For example, in Switzerland, 27% of the population is iron deficient, and that's mostly young adults and women. So as you see here, the recommended daily intake of iron for an adult male is about 8 milligrams, for a female is 18 milligrams. If you eat a bowl of rice, of cooked rice, you get about 0.3 to 1.2 milligrams of iron, depending on the rice variety that you eat. So you see that just eating rice is not sufficient to give you the iron content that you need for a healthy diet. Therefore, we decided that we want to increase the iron content and also zinc content in the polished grain. So this is actually the rice grain that we eat. So we remove the seed coat, which is actually quite healthy. It contains a lot of nutrients, but this is not what we eat. So we polish the rice, and this is the white part here. This is called the endosperm, and this is what we eat. So you cannot breed rice for increased iron content because there is no germplasm available to do that. So the only way to increase the iron content is by genetic engineering. So as you see here, the polished grain iron content is about 2 micrograms per gram dry weight. But what we would like to achieve is a target iron content of 13 to 15 microgram per dry weight. And we have accomplished this using various strategies. So a central aspect to our strategy is actually storing the iron in the endosperm. So that is a polished rice grain in a protein complex called ferritin. Ferritin is a protein that all organisms have. We have a lot of ferritin in our liver, for example, to store iron that plays a very important role, for example, for oxygen uptake in our blood. So ferritin is usually, rice also has ferritin, but ferritin is usually not expressed in the endosperm. So we engineered rice to specifically express ferritin in the endosperm so that we have a store where we can keep the iron. Oops, this was too fast. Can you go back? Oh. Cannot go back. So there we go. But we have also used other strategies to increase the mobilization of iron in the plant to help bring the iron to the endosperm. And of course, we have also helped the plant to increase the uptake of iron from the soil where it is very abundant in order to bring the iron to the rice endosperm where we then store it. So in the next slide, I show you, I cannot show you all the data because of the little time that we have available, but I show you the data to indicate that we have achieved this. So here you have a mega variety called IR64 that's eaten by a lot of people in Asia. And so in this variety, we have actually been successful in increasing the iron content and also the zinc content, which goes usually along with the iron. Here you see the IR64 that is currently eaten by the people, and you see the iron content, which is very low. And in the gray bar, you have the polished rice corn, so the polished grain. And you see that we have now various varieties with iron levels that are very close to the target. Okay, so of course, in a genetic engineering strategy, you get a variety, but many of our lines have achieved iron levels that are sufficient that with a bowl of rice, you can get the amount of iron that your body needs every day. The same for zinc. We were also able to increase the zinc content, and we have now rice varieties that are very nutritious for both iron and zinc. I wanted to show you one example, which is interesting because we have also been able to combine the increase in iron and zinc in the polished rice grain. So here you have Nippon Bara. This is another variety of rice. And you see that this is usually white, but we have been able to also increase the amount of beta-carotene, which rice usually does not produce. And beta-carotene is a very important molecule for our health as well, because when we eat the beta-carotene, this beta-carotene in our body is converted into vitamin A. So we have been able to combine our iron and zinc traits. So here in these two charts, you see the iron and zinc. And then we have also been able to increase the amount of beta-carotene. This is shown here. So Nippon Barro usually does not produce any beta-carotene. We have been able to engineer the rice to increase now iron, zinc, and beta-carotene, and therefore this rice now looks yellow. So we essentially have a multi-nutrient rice that we can now hopefully use for an improved diet for people who usually eat rice. So we have been testing this in Taiwan. So this is our rice field in Taiwan. And I just wanted to share this piece of data with you because in several years now, we have tested our varieties and we have found that the trait is very stable. So here you see, for example, the rice that has iron, zinc, and beta-carotene. And so we are very happy now that we can actually breed these traits into various rice varieties from countries like Bangladesh, Indonesia, Philippines, and so that we make these novel rice varieties, these healthy rice varieties, available to the public. Of course, this is genetically engineered rice, but that's the only way you can do this. And I think the young people in the audience, they will understand that that this is necessary as a way to achieve a healthy and nutritious rice. So let me also tell you just a few words about cassava, because cassava is also very important for as a staple crop for Indonesia, because the starchy root is eaten. So this is me right now in our cassava field in Taiwan, where we're actually testing cassava. And one aspect that we wanted to accomplish in cassava is to develop cassava varieties that do not contain amylose. Amylose is a part of the starch, is a molecule in the starch that gives the starch its gluey consistence. But for industry, this is actually not very good. Industry, for various industrial applications for starch, they would prefer a starch that has only amylopectin. So this is this highly ordered structured starch and not the amylose, which is here shown in blue. So we know the enzyme that produces the amylose. This is the granule-bound starch synthase. And here you see how the protein targeting to starch. So this is a shuttle protein that brings the GBSS to the growing starch granule to produce amylose that, in addition to amylopectin, is then included into the growing starch granule. So one way to get rid of the amylose is then to knock out the GBSS, and we have actually used CRISPR-Cas. So many of, or most of you are probably now familiar with CRISPR-Cas. So this is an enzyme that can make double-stranded breaks in the DNA, and by the repair process that then the plant or the other organisms use, you try to repair the DNA, and often in that repair process, you also introduce mutations. So we have targeted specifically the GBSS molecule, so the DNA, the gene that encodes this enzyme, and we have introduced mutations and shown that that this CRISPR-Cas approach actually works to knock out the GBSS. We have combined this strategy with a protein that causes cassava to flower early. And I'll show you why that is important. But before I do this, I wanted to show you that we now have varieties, cassava varieties, that do not contain amylose. So it is the amylose in the starch that when you stain the starch with iodine, it makes it turn blue, okay? But here you have now starch granule that you cannot stain with iodine because they don't contain amylose. And here you see also that these lines that we have produced with CRISPR-Cas do no longer express the enzyme. So now that we have also a gene in the cassava plants that allow us to flower early, we can actually get the cassava to flower in the greenhouse, which usually it doesn't happen in Zurich. And we can do actually genetic crosses and then cross out the CRISPR-Cas construct so that in the end we have lines that have the mutation in the GBSS gene, but no longer the construct, the genetic construct that you needed to introduce the mutations. And that was actually a very clever approach because this allowed us to breed cassava with new starch properties very rapidly. So it took us 2 years to accomplish this. If we would have done that by a conventional way, so mutagenize cassava, look for the mutation, and then you need to do a very lengthy breeding cycle, back process to keep the mutation, but eliminate all the other mutation that you get with conventional mutagenesis. So that takes you 6 to 8 years. So we have here with our approach an enormous time saving of 6 to 8 years. And we have cassava varieties that are of interest for industrial applications. So I have shown you 2 examples of our research, how we improve the nutritional and the industrial application of 2 important crops for Indonesia. And I hope that it gets the young scientists in the audience excited about this. And of course, I have had great teams at ETH, and I encourage you to contact me if you have questions about our research. Thank you very much, and thank you, Ima, for inviting me to this interesting meeting.